Okay, so first of all, we are going to explain to you the method used to evaluate the environmental impact of products and services, and then we are going to tell you more about the sustainability aspects of proof of work Ethereum, proof of stake Ethereum, the merge, and the Dencun upgrade, and then we are going to close our presentation with some summarizing thoughts. Now, let's try it again. I push the button. Yeah, it's not working. Yes, okay, yes. Now it works. I don't know why. Thanks. So, the life cycle assessment is the standard method used to compute the environmental impacts associated with a product's life cycle. And as you can see, the steps of a product's life cycle are the following. It can be divided into the raw material extraction, that is followed by the manufacturing and processing, and then the product is transported to the retailers, where then it's sold for the consumers. Then they use it, and then they can dispose of the product, or they can bring it to a recycling center. There are many different environmental impacts a product or service can cause during its life cycle. These can be connected to the material and energy input, or to the emissions to water or air, soil, and so on. And a few important examples of environmental impacts are the energy consumption, the associated greenhouse gas emissions, the water usage, and the waste generation. Should work now. Okay, let's try it. Yeah, great, thank you. And in connection with blockchains, there have already been a few attempts to conduct a lifecycle assessment, especially on Bitcoin and Ethereum. Since blockchain is a digital product, its lifecycle assessment is based on the hardware and software used to operate them. Currently, the most studied impacts are the energy consumption and the greenhouse gas emissions, especially in the use phase of a blockchain. A few researchers also try to estimate the energy consumption in the production phase, which is essentially the production of the mining device or other hardware used for operation. Due to the lack of public data on specialized mining hardware, it is extremely difficult to estimate the environmental impact of the production of every single part of mining hardware. And since usually there is no need for specialized hardware for validation and node operation, the range of hardware that can be used for a blockchain like Ethereum is even wider, so it's even more difficult to estimate the environmental impact. And depending on the country in which the hardware used for the blockchain is produced or operated, the greenhouse gas potential of a blockchain will be different. A challenge by this calculation is that it is difficult to find trustworthy data on the location of every miner or node operator. And to tackle this, many researchers use a global average emission intensity, or make different assumptions on the location of the nodes and on the location of the users. So in most studies, only the use phase of a blockchain are estimated, whereas the energy consumption and the greenhouse gas emission estimations of other life cycle phases, like the transportation, the usage and retail, and the waste disposal are ignored, cannot be calculated correctly. And the least studied impact categories of blockchains are their water usage, the associated emissions, and the amount of waste generated and recycled. So the main reasons for the lack of research in these impact areas, as I said already, is the lack of data on hardware, geographical location, and on the blockchain users and operators. And this lack of data is actually not only a potential issue with blockchains, but also with other products and services. But due to the decentralized nature of blockchain, it is especially significant and difficult to solve. So in this short introduction to lifecycle assessment, we mainly discussed one important aspect that contributes to blockchain's material and energy consumption. Oh, sorry, this is this slide. And as you can see on the table below, there are other driving forces behind the energy consumption of a blockchain. The energy and material consumption is driven by the hardware and software, but also by the consensus mechanisms and the redundancy in the blockchain's architecture. And all of these aspects are intertwined with each other. So let's continue our journey with discussing the implications of the consensus mechanism. So Ethereum was originally launched as a proof-of-work consensus mechanism, just as Bitcoin. But how does this work, and how do this affect the environmental impacts of Ethereum? In a proof-of-work system, miners verify transactions and add new blocks to the blockchain by solving a complex mathematical puzzle. And the mathematical puzzle is, in a sense, the task of solving a hash function by a trial and error process of finding the right nonce, which is an arbitrary number. And the hash function, or hash algorithm, is a cryptographic function which, in a sense, translates an input into a unique and deterministic set of characters. And the output of this cryptographic translation is the so-called hash. It is highly unlikely to get back to the original set of characters from this hash. So when the generated hash of the block and the nonce are combined, they are hashed again together. And if the result is less than the so-called difficulty, the block has been mined and can be added to the blockchain. If it is more, the miner has to try again with a new nonce. And the larger the computing hash rate of miners in the network, the more the difficulty increases to keep the block time constant. And after a miner solves the puzzle correctly, he communicates the block to the others, and after it is validated by others as well, it can be added to the blockchain. And the network hash rate is measured in terahash per second, and it is essentially the number of calculations or hashes created per second on the whole network cumulatively. This measure gives us a clue about the electricity invested into mining. So the results of proof-of-work Ethereum. A common issue with proof-of-work blockchains is that as hardware becomes more and more efficient in terms of hashes created per second, the difficulty of solving the puzzle has to increase constantly to keep the block time. And as it can be seen on the figure on the right, this was also the case for proof-of-work Ethereum. The network difficulty on the upper figure goes hand in hand with the annualized electricity consumption of Ethereum. And another source of electricity consumption in proof-of-work Ethereum, besides the mining, are the execution of smart contracts. But relative to mining, this is only a negligible amount. The table on the left compares the results from the studies from the University of Cambridge and from the Crypto Ratings Institute with the estimates about Bitcoin. The analyzed electricity consumption shows the total yearly electricity consumption of the whole Ethereum network and assumes continuous power at the rate measured on the 14th of September, which is right before the merge. The analyzed carbon footprint corresponds to the total greenhouse gas emissions in the period of 1 year, assuming a constant emission rate. The estimations are from the University of Cambridge and from the Crypto Ratings Institute. So compared to Bitcoin, both the analyzed electricity consumption and the carbon footprint of Ethereum were around 4 times smaller, but the number of transactions on Ethereum were 23 times larger. And due to the constant increase of energy consumption, Ethereum had to find a way to become more sustainable, and this way was the change from proof-of-work to proof-of-stake. So the main motivations behind the merge, next to the sustainability aspects, were the need to increase scalability and to increase transaction speed. And it started in December 2020 and lasted until the 15th of September 2022. Yes, and the merge is called such because the Ethereum mainnet was merged with the Bison chain, where the proof-of-stake consensus mechanisms had already been tested previously. As the figure on the right shows, the merge had a huge impact on the environmental impact of Ethereum. According to the Crypto Ratings Institute and the University of Cambridge, it led to a 99.9% decrease in energy consumption and carbon footprint. And all this was due to the change of consensus mechanism, which defines the hardware and software used on the network. So through the change of consensus mechanism from proof-of-work to proof-of-stake, essentially, the way of providing security on the network changed from providing it through work, electricity-consuming work, with, instead of that, it is provided with stakes, financial stakes. And this led to the disappearance of the work-related electricity consumption, obviously. Specialized hardware is also not necessary anymore to secure the network, and the remaining electricity consumption is essentially caused by the execution of the smart contracts, the simple hardware by the electricity consumption of the much simpler hardware that has to be used, and by the softwares, so the client's electricity consumption. And the result is a drastic decrease of environmental impact, as I have already mentioned. And and on the table on the left, you can see the environmental impact results estimated by the University of Cambridge and the Cryptocarbonetics Institute, and the numbers of PayPal as a comparison from 2022. So let's first focus on the comparison of pre- and post-merge. The numbers pre-merge are those estimated the day before the merge, whereas the numbers post-merge are those estimated the day after the merge. And depending on the study, the analyzed electricity consumption was reduced by a factor of 8 to 10,000, whereas the carbon footprint was reduced by a factor of 12 to 13,000 after the merge. And when we compare these results to PayPal's climate report from 2022, we can see something even more interesting. At first sight, before the merge, Ethereum's analyzed electricity consumption was around 80 times larger than PayPal's, and after the merge, Ethereum's electricity consumption became more than 100 times smaller than that of PayPal's. So if you compare the carbon footprint of the two, we see an even greater difference. According to PayPal's reported carbon footprint from Scope 1 and Scope 2 emissions, they emitted 517,600 tons of CO2 equivalent, and it is around 690 times larger than that of Ethereum's emission post-merge. So it is also important to compare them in the dimension of transactions, so what is the utility, essentially. And if we calculate the yield number of Ethereum and ERC20 token transactions with the help of gas fees, we get 1.7 billion transactions, Ethereum transactions, and 580 million ERC20 transactions. And compared to these, PayPal achieved 22 billions of transactions. If we break these numbers down with the yearly electricity consumption and carbon footprint, we see that the PayPal transaction needs around 10 times more electricity than an Ethereum transfer. And also in terms of carbon emissions, we see that with the PayPal transaction, 23.2 grams of CO2 equivalents are emitted, which is equivalent to around 116 Google searches. That's a fun fact. And it is more than 40 times larger than the half grams emitted through an Ethereum transaction. So these numbers show clearly that the merge actually, so that after the merge, Ethereum actually became a greener transaction network than PayPal. And now I would like to give it to Matthias Hafner, who is going to tell you more about the Dencun upgrade and the summarizing thoughts.
Thank you very much for this very nice overview of the current state. So I'm going to talk a little bit about the next steps. So we have seen like that the merge already reduced a lot of the environmental impact. Now the question is what other factors do drive basically the environmental impact of Ethereum. If we go to the next slide, I want to talk a little bit about the Dencun upgrade. So what was the Dencun upgrade? It consisted of 9 EIPs. Most importantly was proto-danksharding. I think you have already heard of it. Basically, it introduced blobs. So these blobs is basically a more efficient way to store data, in particular transactions of layer 2s. Of this second layer of transactions that makes it more efficient basically to conduct transactions. And why are these blobs more efficient to hold transaction? Well, one main reason is because they are stored only for a temporary time and not forever, which makes it cheaper to conduct transactions on layer 2s. So this basically reduces L2 fees, and overall what we see before the merge was highly concerned about the consensus mechanism, proto-sharding, danksharding, and L2s as a whole, basically the evolvement of conducting transactions not only on the layer 1 but also on the layer 2, tackles basically the redundancy problem. So with redundancy, we mean that in layer 1, every transaction is basically recalculated on every node. So in a centralized system like PayPal, we only have a few redundant calculations to ensure the system. Basically, the trust of the central entity ensures that it's correct. In blockchains, we have this redundancy by default because many different nodes, basically all nodes, basically calculate or ensure that the transactions are correct, more or less. So this obviously this requires more computation. However, layer 2 is a possibility to reduce this redundancy in a way that not all transactions are calculated by all nodes. We have like a second system where some transactions are aggregated and stored in an aggregated way. And if we look now at the implication, as I said, it allows L2 and proto-dank sharding, allows basically for a more efficient allocation of the resources, so to say, and reduces, I call it, unnecessary redundancy. So, because these effects, if we look particularly at optimistic rollups, which are quite centralized in the sense of that the aggregation of the transactions is quite centralized. There are mechanisms to check for it afterwards, but the aggregation is quite centralized, so it's highly efficient. So the costs, the computation costs, they come basically for optimistic rollups for storing this data on the layer 1. And therefore we can use the fees as an approximation for the consummation, computational consummation. And if we look at the prices of L2s, then we see that they are now roughly, for optimistic rollups, they're roughly, for L1 at that point in time when you take it, these are linearly scaled. They were $2 for optimistic rollers. At the same time that we captured this, there were 2 cents. And this ratio is in line over time, so maybe it can fluctuate both, but because they're highly dependent on each other, is mainly about 100 times. For other types of rollups, so for Z-key rollups, this ratio is lower. But so to say, when we look at L1 and L2 with optimistic rollups, or L2 in general, we can say that basically these L2 make Ethereum 10 to 100 times more efficient for today. And if we look at the Dencun upgrade specifically, it reduced the L2 fees by 80 to 9%. So basically 90% of this reduction is due to the Dencun upgrade. And obviously, Dencun upgrade was integrated 30 days ago, so that might change a little bit these numbers. So basically, coming to that, to the discussion, let's look at Ethereum's strategy. So the Dencun upgrade basically is the start of the search area of Ethereum, and Ethereum, the goal of Ethereum is basically to increase the scalability to 100,000 transactions per second. So Ethereum's strategy is to increase the scalability. And if we look now at the main sources identified over our journey, these are 2. So once we have the consensus mechanism that was tackled with the switch from energy to assets as a security, which reduced the environmental impact immensely by 99.9%, so making it already greener, or if we have at least at par with today's transaction systems, payment systems. So the next step is redundancy, as we identified, and here that we see that these temporary data storage, so the proto-dank sharding, and aggregated verification, so layer 2s, reduced the impact again to roughly 90 to 90%, so making it even greener. So basically, if these transactions are conducted on layer 2s, so this technology is greener than today's payment systems. So if we now compare, so this is good what we basically see. If we compare now Ethereum strategy, which goes beyond, so this we haven't reached this 100,000 transactions per second, but if we compare that basically with the direction, then we see that it's aligned. So basically, the Ethereum wants to make more transactions per second, so more efficient. So this helps also the environment, because that means that less computation are needed to store this transaction. So Ethereum strategy is aligned with the environmental goals. What holds the future? I think there we, as I said, there is more going on with Dencun, so more involvement of Ethereum, so to make it more efficient. Then we have what else can be done is basically more separation of tasks. That also helps the efficiency. So one is basically this proposer and builder separation, which is discussed now. And obviously what we need to do, our estimation for L2 and for Dencun was very roughly using the fees estimates, especially with set key rollups. There are also additional computations that come with it. So obviously we need to better understand the impact of various L2 types to have a clear view, basically, how green Ethereum will be in the future. Yes, so that's about it. Thank you very much for your attention.